Okay, good morning to everyone, and we're finishing up week 2 of the first part of the semester. It's amazing, 2 weeks already out of the 15. And this is a Friday, a nice foggy Friday. Makes it nice coming into an algebra class. You get warm and toasty and a new appreciation for taking algebra that you've never had before. We had homework on ratio and proportion. Is there anything that you need to ask about that homework? Ratio and proportion. Go ahead. Just spit it out.
Your word problems are driving me crazy. I don't understand where to put what and how to keep them together so that I get an answer that's correct.
So pretty much the essence of that is word problems suck and I don't know where to put them. Is that a paraphrase?
Yes.
Okay.
Absolutely.
Well, before we get into that, Susan, we were listening to CC&R, right? What was the selection in that?
Side of the road.
Side of the road. That's where you want to be not
That's where we're
in the
going
fog. Well, do you have a particular problem you would like to address on this word problem kind of reaction?
The last few that we did, which is, well, 45, 47, 59, 60, 61, 60. Oh, 62 I got.
Okay, so 61 and 62, for example, that kind of problem?
Yes.
Okay. Let's maybe focus there. Now, part of the reaction to word problems, again, is a kind of continuing one, getting past the words and trying to interpret, translate, and we have a tendency, I think at times, to jump into a word problem solution too quickly, and I've talked about that. Reading a word problem a little bit like you would Dagwood. You read through it quickly, sort of scan it, and then expect to have insight. Now, even the cartoons, I find myself having to read twice just to figure out what was being the point. And a word problem, certainly more than that. And oftentimes in word problems, we are placed into a new territory, particularly in 61. Let's look at the document cam for a moment. Now, this is a problem in the physics area, and if you were to take a course in physics, you would learn a little bit more about this. You would hit this problem in calculus. And so we have a distance a spring stretches is directly proportional to the force applied. Okay, now we need to interpret something there that I didn't do an adequate job of yesterday, and that's talk about direct proportion. If you say something varies directly, it's really saying that y is equal to kx. Y varies directly as x says that there's some constant that you can multiply times x and get y. So we talk about direct variation. And I realized after the hour was up, did not cover one of the formulas I had in my mental note that I needed to discuss, and I anticipated that it would probably come up as part of a question. So let's look at page 130. To say that y varies directly as x is this equation, y equals kx. Something is directly proportional to. Now I'm going to first ask you to focus for a moment on the equation, y equals kx. We talked about equations like that yesterday when we talked about slope-intercept form. So in that formula, k is the coefficient of x, so k would be the slope of the line. There is no constant term. That is, remember we have y equals something times x plus a constant. Well, there's an implied 0, so this would go through the origin as a line. And again, I'm building on past background that I assume you have had in either a pre-algebra or a Math 10. When I say something varies proportionately, if x gets larger, I expect y to get larger. there is another kind of variation that I want to include in contrast, because I think one without the other at the moment is probably not as good as it should be. Inverse variation. Inverse variation. As one thing gets larger, the other gets smaller. So we mean by that inverse. Now, for that kind of problem, x times y is equal to a constant. Inverse variation says as one variable gets larger, the other gets smaller. Direct variation says as one gets larger, the other gets larger. Now, trying to find examples of direct variation are pretty easy. If you have a larger amount of lawn, it's going to take longer to mow it. Now, what about inverse variation? The faster you drive, the shorter the time to get there. Direct variation, the faster you drive, the bigger the ticket. Okay. The more the weight of a vehicle, typically the lower the mileage, miles per gallon. And so that would be inverse variation. Okay. The bigger the engine, the more power you have. Direct variation. So I want you to have a sense of direct and inverse variation, because in this particular problem, the problem involves direct variation. Now, the key here in such a problem is to find the value of k, the constant of proportionality. So typically in a problem like this, you're given a pair of numbers. Notice, 30 pounds will stretch a spring 16 inches. 30 pounds, 16 inches. Now that allows you to go ahead and decide on what? The value of k. So let's come off there for a moment. We have a formula we need to write. Y equals kx. And if you had a little bit of trouble with this one, it's my fault, because I didn't provide you this particular part of the explanation yesterday as we were going through this. So we want to write a formula, y equals k times x. And we are doing number 61. And what do I know about this problem? 30 pounds stretches at 16 inches. So I put 30 pounds, and that stretches something 16 inches. Now, the units aren't particularly critical here, but I am interested in the value of k. So I could argue that k is going to equal 30 over 16. Now, you might decide to include the units, which would be 30 pounds over 16 inches. So I could put pounds over inches. But you also might be inclined to reduce that fraction to 15/8. Certainly doesn't hurt. Not much is gained here. I would be not inclined, typically, to go ahead and try to do this as a decimal. Now let's come back to the statement of the problem. Now the question is, how far will a 50-pound force stretch the spring? Okay. Now, we are using y equals kx, and says the distance, and I have that unfortunately reversed, my x and y, now that I think of it, because the force is proportional to, the distance is proportional to the force. Now I could still solve the problem appropriately just by putting 50 into the equation. Now I have the value of k, and I could solve for x. But if I'm going to do justice to this in terms of the way the problem would be stated in a physics class, I would have been better off saying what? That 16 inches, the distance, is proportional to the force, and have my 30 pounds here. And now, if I'm going to set up my x as the weight or the force, then k is instead going to be what? 16 over 30. It could be done either way. However, to be fair, in terms of how you might see this in a course where you would be doing this problem in physics, it probably is better done in this second case. Now, I'm going to complete the solution either way, just so you realize it didn't matter too much which way I set this up. In the first version, I would have y equals 15 over 8 times x. In the second version, I have y equals 8 over 15 times x. Now, the problem here is which is x and which is y. In this problem up here, the way I've set it up, y is the number of pounds. In the way I've done it here, y is the number of inches. So I'm going to get the same answer either way. Now, back to the problem. If I put 50 pounds, I think that's what it says, I want to know the number of inches. I can stretch the spring. If I have 50 pounds, I'm going to put 50 here. So what I'm going to have in this solution, let's see, I'll do it. Okay, I have two different approaches, so I guess I'll do this one with a brace here. And say y, which is what I'm interested in, will be 8 over 15 times what? The 50. Now, this was going to be pounds down here. The units cancel, and I'm left with inches. Now, to do that, it doesn't lend itself very nicely to a clean solution. I can divide 5 into here and 5 into here. So I'm going to get a 3 here and a 10 here. So I have 80 over 3, which would be 16 2/3 inches. 26, thank you, 26, not 16. 26 2/3 inches. And I have a solution. Now, if I come up to this point and treat it here, this is the other approach, then y, which becomes what? Remember we said that was our number of pounds, so I put 50 here. I would have k, which is 15 over 8, and that is times x, and then what do I have to do? Solve for x, and I have to multiply both sides by 8 over 15, so I'm going to have 8 over 15 times 50 is equal to x. And I'm ending up with the same solution, which is going to be 26 2/3 inches. Same solution. The second approach is the more typical one that's done in physics, and this is referenced as Hooke's law. Now, there's another way I can work this problem that I want to bring to your attention. K is what? Depending on which way I set it up. If I have just in general, y equals kx, let me rewrite it this way. What is k equal to then? Y over x? So I have a proportion. K over 1 equals y over x. And we are saying that that proportion is going to be the same. If it's proportional, the proportion stays the same. So I could say that if I'm going to, again, keep this in mind, this is going to be where x is going to be my pounds, and y is the number of inches. This problem could be done by saying that 16 inches over 30 pounds. Otherwise, this is going to be the same proportion for the spring regardless of what stretching you use, within the limitations of the spring. Now, if you've ever taken apart a ballpoint pen with that real small little spring, and you sort of pull it apart and let it snap together, you can do what? You can pull it so far apart, it no longer retains its elasticity. So there are boundaries here. But then the question is, how many inches, I'm just going to put a question mark there, if you do what? 50 pounds. Now that is a typical what? Proportion problem. And I would solve for the question mark, which we would typically say is some letter. Now, I'm a little bit hesitant to use an X or a Y because I've already used that. So let's just, for the moment, think in terms of solving for the question mark. It would be 16 times 50. So the question mark is going to be 16 inches times the 50 pounds, because we're cross-multiplying. And that's 30 times this, so I divide by 30. And you'll note that what we can see right here and right here in reducing becomes exactly the same solution. So there is certainly two distinctly different ways of doing this problem. From a practical point of view, this technique here, y equals kx, find k, plug in x, get y. So the process, 1, solve for k given information. Rewrite linear equation using k, using the value of k. Step 3, substitute typically the value of x, the second value of x given, to find y. Now, isn't that what you basically did in the process? You used information from the problem to solve for the constant of proportionality called k. That was, if I come over here to the far left, this value down here. Now maybe we can take camera 2, Caesar, if we run over there. Then I took that value of k and did what? I substituted it into the equation, and then the next step was, as I rotate, plug in the value for x and find y. Well, as we now go to camera 2 and look at the process, that is exactly the process we're talking about here in 3 steps. Now, there are a couple things that I've tried to share with you in this week. One of them was certainly yesterday in answering a question about ax plus by equals c and how important it was to solve for y and get the slope-intercept form. That was very important. Today, we have something equally important if you are going to take courses in science. How to do a problem in direct variation. One of the classic examples of this is this spring stretching problem. Another classic example is volume and temperature. As a closed container is heated, something happens. Now, most of you have seen it on the stove, boiling something with a top on it. The temperature increases, the volume stays the same, the pressure gets higher, and pretty soon you have things bubbling over the side of the pot. If you put a container out in the sun and the contents expand because of heat, it can explode on you. Gasoline is one of those things you do not want that to happen to. And so we have a state law that says you cannot place gasoline in what kind of container and put it in your vehicle. You can't put it in a glass container. You have to have a metal container that will withstand pressure. And if any of you have been out mowing the lawn, had the gas can outside with you, the mower runs low, and you try to open up the gas can, usually you hear a poof as the volume that has been contained, the volume inside is trying to expand, and then, of course, you hear it as you open the cap. Well, these are examples of direct variation, and very important examples. Now, the second problem given in that set is a problem about proportionality in geometry. And if you think of a right triangle. I'm going to draw one on the board here just briefly. And we talk about things that you should know a little bit about if you'd had, for example, a Math 10. This is a right triangle. And if this is 3 and this is 4, this is 5. This is the classic 3, 4, 5 right triangle. This is used in construction. If you measure, otherwise you have a floor, you put a wall up, and you measure out 3 feet and put a nail here, and you tag a nail 4 feet up here, and you take a piece of cord and stretch it exactly 5 feet, you're guaranteed that you have a right angle and that the wall will be perpendicular to the floor, which is a nice setup if you're building a house. You can do the same thing for foundations. Now I can draw another right triangle that appears larger than the first, and I don't know if I've done that justice, but this would then, I'd argue, be 6, 8, and 10. Now they're both right triangles, and one is proportional in length to the other for any side. So for example, if I take these two sides, 4 is to 8, as what? 5 is to 10. Does that work? You cross multiply, the cross product. That's to guarantee that it is true. 4 times 10 is 40, 5 times 8 is 40. Therefore, we say that proportion is valid. Now, if I tell you I have two triangles like this, we refer to these as similar triangles as opposed to congruent. Congruent means you put one right on top of the other, they match up. Similar says the lengths of the sides are proportional. So we talk about similar triangles. And I'm just going to use a triangle with the symbol there for representing that. But now, if I tell you I have similar triangles, and I don't tell you what this side is here for the moment. And by the way, with this information and the Pythagorean theorem, you could solve for that side. The Pythagorean theorem says if you square this length, you get 64. Square this length, which is going to give you 36. Add the two together, you get 100. The square root of that must be this side, hence 10. Well, if I write it as my proportion now, 4 is to 8, as something, let's see, I have 4 is to 8, as 5 is to what I don't know, then you can do what? You could let that be x, for example, and just solve for x. Isn't that, in essence, the kind of thing that's involved in 62? Well, I'm going to leave that there, and let's see the kind of problem involved here, because in this case, we don't have, we don't have triangles. We have what? Squares, and so the idea of similarity per se is probably poorly voiced. But the argument is that the perimeter is proportional to the length of a side, in much the way we define similarity in those two right triangles. So if we're going to argue that the perimeter is proportional to the length of a side, what formula would I want to write there? And I'm looking at my time expression. Let's leave that there for a moment. And how do I want to do that? Okay, Caesar, I'm going to jump over here to just this right panel. Perimeter is proportional to the length of a side. P equals Ks. Now let's look at the problem in the document, Cam. In that problem, I'm told a square with a 12 centimeter side has a perimeter of 48 centimeters. Well, if I know what perimeter is, this is sort of a silly problem. But nevertheless, I'm saying 48 is equal to what? K times, and I think it was a side of 12? Now, K12 would be better written as 12K, but for the moment we're going to leave it that way. And so I could now, if I'm going to follow that process I had, argue that K is 4. Now if I know K is 4, I can come back to my original statement and now say P is equal to 4S, which, by the way, you know as the formula for the perimeter of a square. So this is manipulating terminology in a way that's questionable as to its need. If you know the formula, why are you solving for the formula in a way? But now, knowing this formula, we come back to the problem, and the problem asks us what? Well, if you have a square with 5 centimeters, what is its perimeter going to be? So now I come back to the board and say, well, P must be 4 times the 5, which unfortunately looks much too much like the S I had here. And then I'm going to argue that this is going to give me that P is 20. Come back to the problem. And the thing that I have not done adequately here is indicate units. Now this bothered me in some of the homework I was grading, that you were given rather pure numbers in those formulas, and you were finding things like volumes or perimeters or areas. And when you find a volume of 48 and don't realize that it's cubic something, we've done a disservice to you in using a formula. So may I just remind you that volume is in cubic units, cubic feet, cubic yards, cubic centimeters. Area, square feet, square yards, square meters, square centimeters, and perimeter is just the unit itself, centimeter or inches or feet or yards. Okay, and that is something that is really involved here and should have been perhaps stated up here, because this is 12 centimeters and this is still 12 or 48 centimeters. So your formula does include units. And to continue to use them in a somewhat capricious fashion here, like units didn't exist, is a bit on the dangerous side. Now that is looking at those two problems with a lot of time invested in them, because they are important in terms of concept. Now that brings up an interesting general comment I want to make with what we go into in today's presentation. So let's go back to the book for a moment, Caesar. You look at a problem and you have to make a judgment, a classification. What kind of problem am I looking at? Is it a problem in proportions? Is it a problem in integers, like we did the last set of homework problems? You classify the problem, and on the basis of classification, you hope you have a better idea how to solve it. And I hope it takes it out of that general category, I don't know what to do or where to put the numbers. So identifying type of problem becomes, as much as anything, a strategy for success as you do a word problem. Now, are there any other questions on this set of problems that you'd like to address that we are going to turn in momentarily? Yes, Jill.
I did from yesterday is put like the like terms on top of each other, and I thought it works better for me just to get that proportion to go.
You wrote it as a proportion.
Yeah.
Much as we come back here now to the board, where I was doing that in this style. Right?
Except for I put
16 over 50.
Oh, you put,
30
okay,
over
50 over 30 and something over 16. So your units matched up.
Yeah.
That's a good point. I mixed my units there because of the way the problem would be written from here. But yes, remember we made the comment that you can reverse the medians, as they are called, and reverse the extremes and get your units to match up. I concur. So that would be yet another form of solution. But at the same time, you need to appreciate that one technique involved here comes back as we slide over now, where you have your equation y equals kx, that's what's up here. You take a value for x and y and solve for k. Now there are two ways of doing this problem. One should not exclude the other, because you're trying to get some insights about how to do this style of problem. And so writing the equation and solving for the constant of proportionality, that's what k is referred to, the constant of proportionality, is a very important part of your background. So even though you may have done it just as two ratios equal to each other, hence a proportion, you need to understand there is an alternative solution that you need to know exists and understand what's done with that in case you are expected to do that in a subsequent course. It's not a case where there is just one absolute answer as to what you should do. Any other question? Okay, would you be kind enough then, please, to again fold your papers and have your name on the outside and pass them over here to, again, the side to your right. And to those on the right of me, straight ahead. Okay. Just throwing the papers around, right? And we move on to a topic that will warm your heart even more. Let's go to the document cam. More about problem solving. So if you liked solving problem 1, solving problems 2 will definitely appeal to you. Okay. Now the question, how is this set different than the last? And the answer to that is in the type of problems we will learn about. And what's nice about this is you have 3 days to work on the homework. So I give you more, then it's directly proportional to the length of time you have available, how long the assignment is. So if it's a longer weekend, you get more homework. So your desire for that homework is inversely related to the length of time that you have to do the homework. Inverse and direct variation. Now, the classification for these word problems includes a familiar category, distance problems, but with a little subcategory called motion problems. Hence, you may feel motion sickness. You have motion problems and distance problems. Another generic category is a mixture problem, mixing things together. So mixture problems, distance problems, motion problems. There is a classification that I'm not quite as, I don't place it in quite the same serious category. Money problems. Now you say, well, boy, do you have your priorities screwed up. Money's more important than anything else. Yeah, but they're sort of, they aren't the kind of thing that you would typically do with algebra. Let's talk about motion problems first, because they are related to distance. We already know the formula for distance. It was the dirt equation, right? D equals RT. Now, you do need to know something about how you find distance relative to having rate and time. And I'm going to take an example just so you have something that you can reference, and it's fairly typical. We're on page 142. Okay, 2 planes leave LA at the same time. Now, if we talk about problems, have you been at an airport? 2 planes leaving at the same time? They take turns, right? So to have 2 planes leaving at the same time may challenge your sense of credibility. And they're going to fly in opposite directions at the same time. But understand that this is something that you would like maybe for this problem to happen, and we aren't going to worry too much if there's 30 seconds difference in takeoffs. Now, one heads north and the other heads south. That is simply saying they are going in what? Opposite directions. It could just as easily be east and west, although you would challenge the location of San Francisco and San Diego relative to LA. Both planes are flying in opposite directions, and there's a neat diagram, better than I would draw, because they have, well, I don't know. Those are pretty sick-looking planes. But one's a blue and one's a green, and one's slower and one's faster. Okay? Not unusual. 2 planes having different flying speeds. question. What are you told about the information in this problem? Let's see if I can get it stated here. Okay, the San Francisco plane going to San Francisco is going to go 50 miles per hour faster than what? The one to San Diego. Now you'll note a very time-honored form of solution here. Draw a table, and a table may help you organize the information. We said this was a dirt problem, and notice we have R, T, and D in sort of reverse form. We usually put D on the left side. But we are arguing something about distances, so that's why you find distance on the right side. But slower plane, faster plane, do you have to create this table to do the problem? No. Do you need to draw a diagram? Yes. The diagram can accomplish what the table is attempting to do for you. Now let me again see if I can get the book at about the right height I want it so the table can stay there. Okay, let's come back to that table. I'm going to go to the now side panel, Caesar, and I'm going to use a straight edge to represent something about how the planes are separating. So for the sake of argument, we're going to put LA as a dot, with no disrespect to our friends in the South. Now, in a sense, the two arrows would be different lengths possibly. All we know is that one plane goes faster than the other. Now, is San Diego closer to LA than San Francisco is to LA? Would we agree with that? So the way I have this is SD here and this is SF here. Okay? Now, what do we know? Anything from the problem? Let's go back to the problem itself for just a moment. I think there's some information that I can't see there the way it's written. Let me look off of a book here just for a moment. It tells us something about that at a certain time, okay, the planes are 275 miles apart at some time, correct? At the end of 1/2 hour. So at t equals 1/2, then we're saying that this total distance here is what? 275, correct? Now, what do I know about each of these distances? They are rate multiplied by time. So I know that one of them is r times t, and the other is what? R plus 50 times t. Now, which is the faster plane? The one going to San Francisco? Okay, so whatever this rate is, r plus 50 is the rate we're going to use going to San Francisco, where r is just the rate we go to what? That we go to San Diego. So if that's all I had, I know this distance and this distance involving the same times would add together to give the 275. Now I'm supposed to create an equation out of this, and we are expecting to have only one variable. Well, if I know t, then I'm going to expect to solve for r. So I could look at this and argue that t should be 1/2 here and 1/2 here. And by simply looking at the diagram, I'm hoping that you can see that that 275 is going to be then, I'll do it in the same order, although I would have been better off putting the 1/2 in the front, plus r again times 1/2. Now once I get there, I have my equation. Now let's look at the table again. Same argument. The 1/2 is substituted for t, and you have in the right boxes the same two distances I have on the side board. And then let's come off there for a moment. I'm going to slide down to the equation and the solution. Now again, there's a question here of just what is the best approach. But there's that same equation essentially I had on the sideboard on the monitor now. I would have been inclined likewise to multiply everything by 2. That's what's done in that next line, and you can see the solution where we ultimately get down to what? 250 mile per hour for the plane to where? Okay, to San Diego. We're going to be at 250 and 300 miles per hour to San Francisco. And that makes sense to me because you're wanting to get to San Francisco, and it's a longer distance, and you'd like to get probably keep the times down, and maybe you're not fighting wind problems, or you just may like San Francisco better. Now that's a type of problem, motion problem, and it's very typical. But they can really change in the way that you state the problem. Now this is probably the most straightforward of the problems. Two distances add together to give you what? A total. Now if I had two cars traveling toward the East Coast, I might want to know if their speeds are known, how long would it take them to be 300 miles apart? Now my point there, you have two distances that would be subtracted as opposed to added. The way the problems are stated are going to dictate how you approach it. Now, let's look at a variation on this problem with the diagram. This is on page 147. You have a Portland and St. Louis connection, and they are flying to what? Well, they're going to meet at some airport, you hope, because if this is midair, this is not good. So when it says, how long will it take for them to meet, let's not assume this is a midair collision. But notice now, instead of the planes starting at the center point and heading in opposite directions, they are approaching each other, okay, and that is a different issue. But notice as I slide this over just a little bit, again, you have a table that allows you to make a decision as to what kind of equation you want to write. So you're given quite a bit of help here, is what I'm getting at. You have to be also thinking as you do a problem like this, can you set it up without that table first? Because the table will not always be given to you. This is an aid at the moment to help you see how the solution should be done. Okay, so much for a motion problem. What about what is cataloged now as just a standard distance, rate, and time problem of the type given on page 140? Now, this is a rather fascinating problem because I really like the car. Now that is one neat antique. Okay, recently we had the opportunity of going up to the Calaveras Big Trees and spending a day. And when we were there, in fact, we spent an evening, I guess it was, and stayed over in our trailer, and a whole group of car buffs driving cars that had to go back to the turn of the century, previous century. Really neat to hear them clunk along. And then I was very pleased that I had a 2002 vehicle that I was driving as I went home. But let's see what we have here. We want to find distance, rate, and time. Okay. And so what you're given here are just some problems illustrating it. Sound travels at 1,088 feet per second at sea level at 32 degrees Fahrenheit. And so if you're given information about R and T, you can do what? You can multiply them together to get distance. I don't think that's particularly exciting, but just a comment, that is a type of word problem using the formula that we had before. And I think you see the difference between those two type of problems as being very different in complexity. Mixture problems. 136. This is example 2. I'm going to try to put this in a little better category here for a moment. But you start with the idea that a chemist needs to have 20 liters of a 40% acid solution. And you have 50% and 70% available. No, I didn't say that right. You have 40 and 70 available, and you're going to do what? Get 50%. So the point being, you have two solutions, one too strong, one not strong enough, and you put them together to create what? Something that's just right. Now, do you have to be a chemist for a problem like this? No. Saline solutions are used in hospitals. Let's say instead of an acid, we just say you have a 40% saline and a 70% saline, and you want a 50% saline. To make it a little bit less intimidating to take it out of the chem room and put it in a hospital environment. We could talk about mixing cocktails at home for the happy hour. You have 40 proof and you have 70 proof, and you'd like to create a 50 proof drink. Okay, so why you do that, I have no idea. Okay, but you can certainly make it a little more interesting. Now, what is the premise here? When you mix two things together, you don't lose something in the process. Okay? The strength, the amount of salt in the mixture doesn't suddenly change. You want to have the same amount of acid in the result at the end that you did with the two different things you put together. When you say you have a mixture, we assume typically distilled water. That's the medium in which you place a substance. So when you create a saline solution, there's a certain amount of salt there. It just happens to be in a liquid form because it's dissolved in the water. It doesn't change the amount of salt there. Well, that, in a sense, is what is involved with the solution that's presented in this little table again at the bottom of the page. Now, the argument is you're going to use 40 and 70% solution. Okay? Now, in this case, you're given some information that you're going to put 20 liters of 40% with an unknown amount at 70% to get what? A 50% solution. Now, the right column that you're looking at on the screen is the amount of acid in each of those parts. If I have a 70% solution at X amount, the 70% of X gives you the amount there. Let's try the other one a little bit easier. 40, is this liters? Am I right there? Okay, a liter is like a quart, nearly. So I have 40 liters like 40 quarts, 20 liters like 20 quarts at 40%. I didn't catch where the decimal is. I'm going to leave that there, and I'm going to go to the sideboard so we can write the numbers down. I have 20 liters at 40%. So 20 liters at 40%. Now the question is, what does that mean? How much acid do you actually have? Or how much salt do you have in a saline solution? The product of these two is the amount you have. Now I'm going to put X liters at 70%. So how much do I have there? Well, I have 0.70 times X. I don't need the parentheses there. Now I'm going to put that together. And I'm telling you that when I join it together, and I'm going to put a brace there. When I join it together, what am I going to have? A 50%, right? So now I ask, the amount of acid here, or the amount of salt in saline solutions, is going to be exactly what I have over here with a 50% solution, but now it contains what? x plus 20 liters. The box isn't so important as it is to understand what you're setting equal. Now, the equation drops out of this quickly because the two amounts together are going to give you 0.40 times 20 plus 0.70 times x, and that must be what? Just your 0.50 times x plus 20. Is it necessary to leave these two zeros in? No. But my suspicion is you're going to be a lot more comfortable with percents as 0.50, 0.40, 0.70 than you are to say 70% is 0.7, which is technically correct. It just doesn't feel comfortable. What is your first step here typically? Clear the decimal points, multiply by 100, and solve for x and answer the question. Now that's a mixture problem. So this went under a category of mixture. And as we slide over, this one goes under the category of motion. Now there's a lot of similarities between how those are done, but they are very different. Leave that one up there for the moment. Motion and mixture. And each type of problem is uniquely done with the same technique. So if you can do one mixture problem, the hope is you can do what? Know how to approach other mixture problems. But the wrinkle in this is to know what to set equal. And that gets a little bit more difficult as we go along the course. Motion problems, you're typically setting the sum of two distances equal to something. And in a mixture problem, you're saying the amount of whatever is in the water or alcohol base is going to be the same whether you leave them apart or put them together. One of the classic problems in mixtures is antifreeze in your radiator, and you know how much antifreeze you have and then how much water do you need to add to get at a certain percent. That's a mixture problem that's a little more difficult than the one we just did. Let's look at think about the type of problems we've had so far in terms of categories. We've had direct proportion. That's where we started. We have had a motion problem, a mixture problem, a problem about integers or numbers we did the other day, and a type of problem that's called geometric, where we looked at information given to us about something geometrically. I remember those were the problems about complements, supplements, and such. Trying to decide how I want to. This money problem, page 138. I'm not just sure how I want to tie this together. Mixture problems are a very fundamental category. Now, in a sense, a money problem can be thought of as a mixture problem in the way that if you tie nickels, quarters, and silver dollars together and make a problem of it, that's called a money problem. And the argument is the number of coins times the value of the coin is the total value of that coin. It's sort of a no-brainer in a way, but as we come off there, you get contrived problems. And I have some mixed feelings of my own about the type of problems we do in algebra. Some of them are contrived and some of them are meaningful. A money problem at times seems contrived to me. A problem with mixture is not contrived because you do deal with those kinds of problems as you do motion problems. But if you look at the example here, I think maybe you'll understand what I mean by contrived. A teller, this is a bank teller, has 25 more $5 bills than $10 bills. So what? And who cares? Now, the argument is, if you know how much money they have totally, can you tell me how many of each denomination they have? Okay. But I can never picture a bank teller doing that problem. Notice the solution here. X is the number of tens. X plus 25 is the number of what? $5 bills. Now you are told something in this problem that the total amount of money is what? $200. So if you think for a moment of what you're seeing there, 10x is the value for the $10 bills, and 5 times x plus 25 is the value of the $5 bills. And if you add these two numbers here on the side, you should get 200. You have your equation. That's not an exciting problem. I think the ticket problem, when there are different price seats and you're looking at how many you might want to sell of each type, is a lot more interesting on 139. It's done in the same style. So keep in mind that the example 5, as you look at it, it's going to be done in a very similar style to what we talked about. What I'm going to give you for homework is a selection of problems that don't reflect, perhaps as well as might be, the variety provided there. And I wasn't sure just how far we would get in terms of the problems, but I'm going to focus now on what we did in our coverage. So as we look at page 147, we have a group of problems there dealing with motion, and they go from 45 to number 54. So we're going to take 45 through 53 odd. So 45 through 53 odd. I'm going to write a note for myself here. And then we had some problems with mixtures. And I'm going to focus on these two areas more than anything else. We have problems that go from about 21 through 25. So 21 through 25 odd. So we have 21 through 25 odd, 45 through 53 odd. And then looking at ticket problems, money problems, that kind of information, seeing if we have something there that we can pull off that would give us a selection. I guess that's more in terms of problems 33, 35, 37. So let's take 33 through 37 odd. Somebody want to take a total of how many I've given you so far now? So it looks like we have 3 there, and 3 there, and about 9. So am I up to about 15 problems? Is that right? Am I close to that? Let's take those problems. Well, I'm figuring 5 minutes per problem minimally, and that puts you in an hour 15, and my guess is you may spend more time than that. But a couple hours seriously spent. Yes, Coda?
That's page 145.
Yeah, 145, 146, 147. So, Caesar, we're closing with CC and R. And what's your choice? Feeling blue. No, feeling sunny. Have a great weekend.